we've discussed the idea of surface area, and you might be wondering how we get this understanding of that. And you say, okay, well, we've got these tangent planes, but tangent planes look like rectangles, so why are we worrying about these 1 plus squareds and stuff? Why can't we just use the area, the regular area? And the answer is that they're not really squares, even though they're planes. They're really determined more by these parallelograms. So if I have a function and I have, or which describes a surface, and I have a point on that, what I can do is I can think about the way the function is changing in each direction and how that change is contributing to the change in the z direction, right? So the partial with respect to x is the partial of the function with respect to x is in a lot of ways determining how the x direction contributes to the rising or the falling of the function. And the partial with respect to y is how the change in y changes the output of the function. It's not quite like that, but wrap your head around it. Just think about it that way. And so the idea here is I want to think of these two vectors u and v. I want to say, okay, if I change a little bit in the I direction or that x direction, how is that change seen? So if this is how much it changes for one unit, multiply it by how much you did change, and you should get the expected output. So if this was 2, that would be 2. And similarly, how much I change in the j direction, in the y direction, how much that function changes in the y direction, multiplied by the actual input, should get you some sort of scaled number that says if I change this much in the x direction and this much in the y direction, how do I get my total change in the z direction? And if you look at it outside of the k and look at these components right there are the components of that total differential delta z. And that's that's the idea, is this is the expected change in z based upon these changes in x and y. So why are we describing that? Well, if we describe each of these as vectors, where u is the vector that's that change in x with the change in z, and v is the change in y with the change in z, then you can construct a parallelogram because each of those vectors are like the sides of a parallelogram. So then, since I have sides of a parallelogram, we actually have a formula, and that's this, the area of that parallelogram. So we're trying to get we're trying to get the surface area, and each little piece we're trying to get these differential surface areas, and those are parallelograms on the surface. They're not actually rectangles. So we have to get the area of a parallelogram. So to do that, we can take the cross product of u and v and then get its magnitude. And that actually gives us the area of the parallelogram, which is a pretty neat result. To simplify our process, what I did is I factored out delta x and I factored out delta y at each point. And what I also want you to know is that if I multiply delta x and delta y together and take their magnitude, I get the area of just the piece of if it were a rectangle. And so you're really getting this area piece of the rectangle, and you're going to get something that's kind of like a sine theta for this thing. It's not quite like that because you have a little bit of scaling there, but the idea here is the output besides this rectangle. If this turned out to be a 1, it would just be a rectangle, but usually it's not going to be, so that's kind of the wobble on it. Anyway, so what you do is you say, okay, well then I'm going to take the cross of these, and these are going to be out front, right? Because the cross product, you can factor out constants, so those are treated like constants. So you end up with this cross product. So it's whatever that rectangular area is times this cross product, and we're going to go ahead and compute that. So if we go down here, we get 1 in the k direction, we get 0, we get negative fx, in the I direction and negative Fy in the J direction. So in the I, J, and K direction, those are your pieces. So therefore your magnitude is, well, it's the absolute value of that delta xi, delta yi times each of these components squared. So I'm going to go and I'm going to start with this one, which is 1 squared plus, and that's really negative f of x at xi, yi squared plus the negative fy xi, yi squared. Well, we saw that is just that rectangular surface area. And then the negatives, because it's squared, the negatives go away. So your final result of your differential surface area is 1 plus the partial with respect to x at the point squared plus the partial with respect to y squared times the differential differential area of the rectangle. And that right there, there's a little more in terms of calculus that you've got to do with a limit to get to the integral form. But fundamentally, this is where it comes from. It's a function of how the parallelograms work. It really puts together a lot of what we've learned in this course about how we can construct things with cross products, how we can use that differential area, and kind of even puts together that surface area integral, or that surface area, or the arc length integral, and kind of generalizes that to multiple dimensions.